Perhaps we have misunderstood Mars for decades. The idea that the red planet once had oceans has existed for a very long time. But most of the evidence was only vague traces seen from orbit. Because of that, many scientists never truly believed Mars once possessed a vast, ancient sea. But then, everything started to change. A small Chinese machine, quietly moving across the frozen surface of Mars, may have just found the missing piece to this entire mystery. You're watching Astrexo. So what exactly did Zhurong discover? Water is something we tend to take for granted until we look beyond Earth. It covers most of this planet, weaves through every river and every ocean, and exists within our own bodies as an inseparable part of life itself. But the farther we move away from this familiar world, that abundance begins to disappear, and across the rest of the solar system, water becomes an extremely rare commodity. That's what makes Mars so intriguing, because all the evidence we have suggests it was once very different. Around 4.45 billion years ago, water didn't just exist. It persisted long enough to take part in the formation of complex minerals. Crystals trapped inside a Martian meteorite have told that story. They could only have formed in the presence of hot, water-rich fluids, an environment that no longer exists anywhere on the planet's surface today. And it doesn't stop there. Even within the fine dust blanketing Mars, scientists have found ferrihydrite, a mineral that can only form when water once flowed and left its mark behind. All of this leads to an unavoidable question. If Mars once had water, perhaps even vast amounts of it, then what exactly happened to it? The traces of water on Mars don't stop at minerals. They are etched directly into the planet's surface. We have seen ancient river systems, flows that vanished billions of years ago, and polar ice caps stretching across areas as vast as entire nations. There, deep beneath the frozen layers, resilient forms of life might still persist, lingering as remnants of a distant past. But that may not be the most promising place. If Mars once had a shoreline, that is where the real story begins. A shoreline is not just a boundary between land and water. It is where ecosystems can form, evolve, and leave their marks over time. Those traces, if they still exist, would resemble biosignatures, scattered clues in a vast cosmic treasure hunt. Enough for us to trace back and reconstruct ancient coastal environments. And the reason is simple. Coastal settings create the conditions life needs most, not abundance, but balance. The water there is neither too diluted nor too chaotic. Organic molecules can accumulate as water evaporates. Mineral surfaces provide platforms for chemical reactions. And energy sources such as radiation, heat, or chemical gradients continuously drive subtle but crucial transformations. In contrast, rivers, impressive as they are far too unstable. They sweep everything away too quickly, diluting materials before they ever have a chance to combine. That leads to an unavoidable conclusion. If we want to find traces of life on Mars, we shouldn't look where water once flowed. We need to look where water once stayed. There was a time when everything we knew about an ocean on Mars existed only on maps and in hypotheses. But now, that story is beginning to touch reality. China's Tianwen-1 mission may have delivered the most compelling, direct evidence yet, not from distant orbit, but from the very surface of a region long suspected to be an ancient ocean floor. For the first time, the data is no longer just inference. It is something that has been touched, measured, and recorded in place, and that makes the entire hypothesis of a Martian shoreline harder to dismiss than ever before. The journey began on July 23, 2020, when Tianwen-1 departed Earth, carrying 3 critical components: an orbiter to observe from above, a lander to reach the surface, and the Zhurong rover, the machine that would directly explore this alien world. After 202 days crossing the cold expanse of space, it didn't just arrive at Mars. It arrived at a specific destination, Utopia Planitia, a vast lowland that scientists have long suspected to be an ancient ocean based on satellite data. But this time, the goal was no longer remote observation. The mission was designed to test everything on site, from surface geology and subsurface structure to climate and subtle variations in the magnetic field. It tracked how dust moves, how the environment affects the spacecraft itself, and most importantly, it searched for traces of water. Not just water that once existed, but water in quantities sufficient to create an environment capable of supporting life. And if what Tianwen-1 has recorded is accurate, then this is not just an exploratory mission. This may be the first time we have truly stood upon the remains of an ocean beyond Earth. There are moments in the history of space exploration when everything unfolds almost in silence, yet the meaning echoes far beyond. On February 10th, 2021, Tianwen-1 quietly entered orbit around Mars, beginning a phase with no spectacular imagery, only system checks, orbital adjustments, and months of preparation for something far more critical. Over the next 3 months, the spacecraft shifted from an equatorial orbit to a polar one, refining every detail as if searching for the exact place to set foot on a world that had never belonged to it. Then, on May 14th, the lander began its descent through the thin Martian atmosphere, where no mistake could be corrected. It touched down, safely. A week later, the Zhurong rover was deployed, slowly rolling across the red terrain, making China the second nation in history, after the United States, to successfully operate a rover on Mars. But behind that moment was more than science. It was a statement. Not just that they could reach Mars, but that they could do it on their own, from launch to navigation to operations, without relying on any external system. And the name of the mission, Tianwen, seemed to be more than a question posed to the universe. It was a declaration that they were ready to seek the answers. Because this was not the end. It was the beginning of greater ambitions, from returning samples from Mars to, one day, sending humans to set foot on this distant world. There are places on Mars that seem quiet, yet hold more stories than anywhere else. Zhurong rover, a roughly 530-pound machine, was deployed in Utopia Planitia, a vast basin formed by an ancient impact, and the largest known basin in the entire solar system. This is not unfamiliar ground. Nearly 50 years ago, The Viking program missions of NASA touched down in this region, marking humanity's first, albeit indirect, footsteps on the Red Planet. But for many years, this place seemed forgotten, until an unexpected discovery in 2016 changed everything. Beneath that barren surface lay not emptiness, but a massive reservoir, ice. A subsurface deposit with an estimated volume of about 7,300 cubic miles. And that opened up a new possibility. This is not just the remnant of water that vanished, it may be what remains of something far greater. An ocean that once existed, then retreated, leaving its traces behind as buried ice. If that is true, then Zhurong is not simply moving across soil. It is moving across the frozen memory of an ancient ocean. To read what lies hidden beneath that silent ground, Zhurong rover is far more than just a rover. It is a mobile laboratory carrying 13 scientific instruments, each one like a sense designed to see through the surface of a world long thought dead. First comes radar, allowing it to peer as deep as about 330 feet below the surface, where light has never reached. Most notably the ROPR radar system, capable of mapping structures buried beneath layers of ancient dust. Then come the spectrometers, instruments that analyze the composition of rocks and soil by reading chemical signatures, from infrared detection to laser-induced breakdown, peeling back each layer of material to reveal the history of its formation. On the surface, optical cameras do more than capture images. They guide navigation, survey the terrain, and connect what is seen above with what lies below. And finally, there are the environmental instruments, sensors sensitive to magnetic fields, space radiation, and climate, including a weather station that can measure temperature, pressure, wind, and even listen to sounds on Mars. It may sound like a set of simple measurements, but when combined, they form a far more complete picture. Because to understand whether this place was once an ocean, you cannot look at the ground alone. You have to understand everything around it. From what lies deep beneath to how the planet breathes, moves, and changes over time. Even on a world hundreds of millions of miles away, humanity still finds a way to look back at itself. Zhurong rover carried a wireless selfie camera, a small device that produced some of the most iconic images of the mission. Those images are not just pictures, they are encoded data, leaving Mars as radio signals, crossing the cold darkness of space for months before reaching Earth, where they are decoded into the vivid frames we see. A moment that feels so close, yet is the result of an almost impossible journey. And from data like this, a bigger question begins to take shape. With all these scientific instruments, what exactly did Zhurong discover about Martian shorelines that previous missions missed? To understand that, we need to return to a very basic principle, one that is ultimately decisive. On Earth, sediment particles do not stay still. They are carried by wind, water, and ice, transported through rivers or pushed downslope by massive ice flows, and eventually settle in calmer environments such as lake beds, floodplains, or oceans. But there is a place even more distinctive, a place where everything is constantly changing, yet leaves the clearest record over time. That is the tidal zone, the transition between high and low ocean levels. Here, sediments are continuously added or removed, shaped by wind, waves, tides, and even storms. And it is this repeated process that creates a defining feature, a gentle slope facing the sea. This slope is not random. It reflects grain size, wave energy, and long-term water levels. Fine sandy beaches tend to be flatter, while pebble-rich shores can reach slopes of tens of degrees. More importantly, these sloping layers can be preserved in the geological record for millions of years. And that leads to a striking idea. If Mars once had an ocean, then the traces of its shoreline may not have disappeared. They could still be there, buried, but never completely erased. Back on Mars, the story begins to shift from hypothesis to evidence. Zhurong rover is not just moving across the surface, it is looking beneath it, sending pulses of radio waves into the ground as if asking the planet about its own past. When those signals encounter boundaries between different layers of material, they reflect back, revealing hidden structures that the naked eye could never see. Each returning signal is a slice of history, a trace of what once happened. But what truly captured the attention of scientists was not the presence of reflections, it was the way they appeared. Their angles.
Radar confirms it. Something is wrong.
Throughout its journey, Zhurong recorded 76 subsurface reflective structures, all tilted in the same direction, with slopes ranging from about 6 to 20 degrees. This is not random. On Earth, these same angles are commonly found in coastal tidal environments, where sediments are gradually arranged by waves and tides over time. And that leads to a possibility that cannot be ignored. What Zhurong is seeing may not be just simple layers of soil, it could be the remnants of an ancient shoreline, formed when water once existed long enough to shape the surface of an entire planet. As scattered data points begin to come together, the picture grows clearer and harder to ignore. Beneath the surface of Mars, at depths ranging from about 33 to 115 feet, Zhurong rover detected a band of structures stretching roughly 0.8 miles, consistently sloping toward lower ground. A formation with order, direction, and pattern. It does not resemble a random phenomenon. It looks like something that was built repeatedly over a very long period of time. And that leads to a question that cannot be avoided. Could this be the evidence they have been searching for? Undeniable proof of an ancient shoreline on Mars. To test that idea, the research team did not look only at Mars, they turned back to Earth. When compared with buried coastal deposits here, especially in regions like Bay of Bengal, the similarities became striking, almost impossible to dismiss. A familiar pattern appearing on two different worlds. And it is not just the shape. One of the researchers put it plainly, echoing what the data was already suggesting. This is a simple structure, but it can only exist if waves are present. And if there are waves, there must be water. There must be a continuous supply of sediment, likely delivered by ancient rivers. And all of these processes must have persisted long enough to build the structure we see today. When viewed on a larger scale, the picture becomes even more complete. Mars, though smaller, is still influenced by the gravity of the Sun and its moon Phobos, and that interaction could have generated tides, slow but persistent motions, enough to shape a shoreline in ways we recognize on Earth. If all of this is true, then we are not just looking at traces of water. We are looking at traces of an ocean that once moved. Science does not begin with belief, it begins with doubt. Before accepting any conclusion, the team examined other possibilities, simpler explanations for the sloping structures detected by Zhurong rover. Sand dunes, lava flows, familiar processes that can create inclined terrain. But when placed against the actual data, things began to fall apart. If these were dunes, the slopes should vary in multiple directions, shaped by shifting winds. If they were lava flows, the patterns would be far more chaotic, lacking a consistent orientation. But here, everything is different. All the reflective signals tilt in the same direction, as if guided by a single force, steady, persistent over time. And it is that consistency that rules out the alternatives. What they are seeing does not resemble dunes. It does not resemble lava. It resembles a shoreline. A tidal environment where waves, wind, and tides repeated long enough to shape sediments in a clear, unified direction. The conclusion becomes increasingly unavoidable. Mars may once have had dynamic coastlines, places where water did not just exist, but moved, interacted, and left its imprint in ways we are only beginning to understand. There are questions in science that never truly disappear. They linger quietly, waiting for an answer strong enough to end the debate. The story of an ocean on Mars is one of them. For decades, scientists have been divided, each side looking at the same data, yet seeing something entirely different. Features once thought to be shorelines were dismissed as imaging artifacts or limitations in resolution, while climate models ran into a deeper problem, a paradox. Because if we go back about 3.5 billion years, our sun was roughly 25% dimmer than it is today. A level of energy that should not have been enough to keep Mars above the freezing point. And without sufficient heat, liquid water could not have remained stable for long. But the pieces do not fit. Models still indicate that at that very time, Mars had rivers, lakes, even oceans. A warmer, wetter world, completely at odds with what we would expect. And that leads to a bigger question, one that has haunted scientists for years. If the heat required to sustain liquid water did not come from the sun, then where did it come from? And the answer, if it exists, may not lie on the surface of the planet at all, but within the atmosphere it lost long ago. When a question has no clear answer, science does not stop. It branches into different paths. To explain the faint young sun paradox, researchers have proposed 3 scenarios, each attempting to bridge the gap between data and reality. The first paints a very different Mars, a world that was warm and wet for extended periods of time. A thick atmosphere, rich in greenhouse gases like carbon dioxide and water vapor, trapping enough heat to sustain liquid water on the surface for millions of years. A world with rain, with lakes, with oceans. It sounds plausible, but when tested in models, the story begins to break down. Carbon dioxide and water vapor alone cannot generate the necessary warmth. Stronger gases like methane, ammonia, or hydrogen could help fill that gap, but they are too fragile, unable to persist long enough to maintain stable conditions. So, a second scenario emerges. Not a constantly warm Mars, but a planet experiencing brief episodes of warming. Moments triggered by violent events such as massive volcanic eruptions or asteroid impacts, releasing bursts of energy and greenhouse gases over short timescales. During those windows, ice melts, water flows, and valleys are carved into the surface. But then the question returns. Were those brief episodes powerful enough, frequent enough to create everything we observe today? Or were they only fleeting moments, insufficient to explain a planet that once held water on a global scale? And then there is another possibility, colder, harsher, yet strangely consistent with many of the traces we see today. A Mars that spent most of its time locked in ice, a frozen world where snow and glaciers shaped the landscape. In this scenario, water did not exist stably on the surface, but only appeared during rare moments, triggered by shifts in the planet's orbit or sudden warming events powerful enough to melt thick layers of ice. Those brief windows could explain why we see both glacial features and signs of flowing water. But once again, the question returns, this time even harder. What could melt that ice often enough, long enough to produce the level of erosion we observe today? There is no clear answer, and that is the problem. All three scenarios, while plausible to a degree, fail to fully explain the climate history of Mars. We have evidence of shorelines, of water, of processes that unfolded over long periods of time, yet we lack a mechanism convincing enough to sustain them. A gap still exists between what we see and what we understand. And it is that gap that leads to a deeper question. Was Mars ever truly habitable? Because to answer that, we are not just looking for water, we need to understand why water could exist there in the first place. It is easy to imagine too far ahead, especially when new discoveries begin to paint a picture of an ocean-bearing Mars. But reality is far more cautious. We are not yet at the point of certainty, and certainly not at the stage of talking about extraterrestrial beaches or distant dreams like resorts on the Red Planet. The picture is still missing pieces, and to complete it, we need more than remote data. We need to touch it. NASA has planned a mission to return samples from Mars to Earth, with a projected launch around 2027 or 2028, and the goal of bringing those samples back in the early 2030s. If successful, it would mark the first time we could directly analyze material from another world, perhaps enough to finally settle a debate that has lasted for decades. But even that plan is uncertain. Budget challenges have pushed the timeline further out, raising the possibility that the mission could be delayed until 2040, or worse, canceled entirely. Meanwhile, on the surface of Mars, Zhurong rover accomplished more than it was ever designed to do. A machine expected to operate for just 93 Earth days instead continued for 358 days, quietly collecting data before entering hibernation on May 20th, 2022. There were hopes it would awaken when light and temperature conditions improved later in the year, but that never happened. Martian dust, fine, persistent, covered its solar panels, leaving the machine silent forever. And in that silence, there is something worth reflecting on. Even as we have come far enough to place our machines on another planet, understanding its past remains a long, slow, and uncertain journey. Thank you for staying with Astrexo until the end of this journey. If this video has sparked your curiosity about the vast universe out there, don't forget to like, share, and leave your thoughts in the comments. Because every interaction is not just a number, but the motivation that drives Astrexo to keep telling stories of space exploration in the most authentic and meaningful way. And if you want to join us on the journeys ahead, be sure to subscribe so you don't miss a single voyage. Because your support is what allows Astrexo to keep reaching further into the mysteries of the cosmos.